Hey, Pre-Calc, we're keeping the party going here in Unit 4B with Day 7. Today we're going to talk about more Descartes' rule of signs. So we're going to pick up where we left off yesterday and talking about some other possibilities that will exist with Descartes' rule of signs. And then once we're done with that, we have really one more major tool to talk about, which is called the rational root theorem. And the rational root theorem allows us to develop a list of possible rational roots that we're going to test in our synthetic division. So instead of me just telling you a root, you're going to be able to have a list of roots to pick from, and we'll go ahead and start testing those. So let's start with an example today of the polynomial p of x equals 2x cubed minus 4x squared plus 2x plus 7. So if this is the polynomial function, what we saw yesterday in Descartes' rule of signs is we start writing p of x, which is just the signs in the original polynomial, which would be plus, minus, plus, plus. So how many sign changes do we see in p of x? We've got one in the beginning and then one from negative to positive. So we have a total of 2 sign changes there. And the other thing we have to write down is p of negative x, where that represents if we were to substitute in a negative x for all our values of x. What we decided is that anything with an odd exponent is going to be changing its sign. So x cubed changes, x squared stays negative, x to the first changes, the constant always stays the same. So you can see at the end here we have one sign change in p of negative x. And what that represents is that those are the max number of positive roots and then negative roots of this original polynomial function. So at the most, we'll have 2 positives, 1 negative, and then finally 0 complex roots. Why do I know again that we have 0 complex for this first case? Because we have to have 3 total roots. So when you have a cubic polynomial, we know that we have 3 roots. If we have 2 that are positive, 1 that's negative, then none of them are complex. Remember, complex is in the form a plus bi. Well, what we have to consider is that there might be other ways that the roots turn out. So according to Descartes' rule of signs, what I showed you in yesterday's video is that the number of roots is equal to this number or less than that by an even integer. So we might have 2 positive roots, but if I decrease this by an even integer, namely 2, that maybe these aren't actually positive roots. They actually could potentially be complex roots of the polynomial. So if I decrease this column by 2, that makes this a 0. Will leave us with 1 negative, and then we'll have 2 complex. Notice how that also equals a total of 3 roots. Something we have to remember about complex roots is that they always come in pairs. When you have something in a plus bi form, if one of the roots is 3 plus 4i, the other root is 3 minus 4i. So knowing that means that this complex column always has to be an even number. And that's why we consider, can we decrease this by an even integer? Because these have to come in pairs, so we can't decrease by 1 and put 1 complex over here for a possible case. It has to be decreased by an even. By the way, you can't take 1 from positive and 1 from negative. It's just not one of the rules. So you have to be able to decrease an individual column, either positive or negative, by 2 to make room for the possibility of, might we have complex roots? Okay, so it's going to turn out to be one of these cases. If I were to graph this, I'm either going to see 2 positive and 1 negative, or I'll see just 1 negative root, meaning that the other 2 have to be complex. Let's try another example, because this takes a little while to get used to. So if I gave you the polynomial 3x to the 4th plus 2x cubed minus 8x squared minus 10x minus 1. Okay, the original polynomial function p of x, I'm going to do this part pretty fast. Just copy the signs over. So it's positive, positive, negative, negative, negative. So you'll notice we only have that 1 sign change. This is the maximum number of positive roots that polynomial function will have. When I move over to p of negative x, we know that for p of negative x, only the odd exponents are going to change signs. So x to the 4th stays, but x cubed changes to negative. X squared stays, x to the first changes. Constant always stays the same at the end. So make sure you do that. Stuff takes a little while to get used to, the p of negative x. But all in all, you should find that you have 3 sign changes there for p of negative x. So when I go to start making my chart for positive, negative, and complex cases, The first row would say that at a max we'll have 1 positive, at a max we'll have 3 negative. And I know that we have no complex because we have to have 4 roots altogether. So if those two numbers already add up to 4, then in the first scenario, there are no complex roots. Can I decrease either of these columns by 2 by an even integer to make room for the possibility of having some complex roots? And the answer is yes. In this example, you can decrease the negative column by 2, so that would bring it down to a 1. The positives can't be decreased by 2 ever, so I'll leave that as 1. And that would give me those 2 complex roots for a total of 4 roots altogether. So that's the only column that I could decrease by 2. And in fact, I can only do it once, right? Because if I decrease by 2 again, I get down to a negative number, which doesn't make sense. But what this tells me is that this function definitely has 1 positive root for sure. It could have 3 negative, but it definitely has at least 1 negative. And then it's either no complex or 2 complex. It's one of those 2 scenarios. Those are the only 2 ways that the roots could turn out. And sometimes this is a really useful tool, Descartes' rule of signs. Sometimes it's only mildly useful. But in the end, it's kind of a checkpoint to say, did I get my roots to turn out in one of these 2 ways? Okay. Rather than doing the whole process again for another polynomial, what if I gave you the first row in a chart? So if I told you that the first row for my positive, negative, and complex cases said 4, 1, 0. Okay. Something that we know about this function is that it's a 5th degree polynomial. We have 5 roots total if we write 4, 1, 0 in the top row, which means that every other row going across is going to have to add up to 5 roots. So the question becomes, can we decrease anything by 2? And the answer is, yeah, it can decrease the positives by 2. So another possible case and scenario would be 2, 1, 2. Maybe we'll only have 2 positives, 1 negative, and 2 complex. Can I do anything else? Are there any other cases? Well, I can't decrease the negatives by 2, but can I decrease the positives by 2 one more time and say maybe there's actually 0 positives? Where do those 2 roots go that I just subtracted out? They can only ever be added to the complex column. So don't ever add them to the middle negatives. Because remember, when you do this step, that's the max number of negatives you'll ever get. But 0, 1, 4 would be a 3rd way that the roots could turn out. So whenever you subtract 2 from an individual column there, they're automatically being added to the complex column. And because complex roots come in pairs, just make sure that you're double checking that those are even numbers always. So these are actually the only 3 ways that the roots could turn out if your first row says 4, 1, 0. I'm going to give you another chart with the first row, and I want you to try to see if you can come up with all the possibilities here. So I'm going to give you that the first row is 2, 3, 0. And tomorrow in class, I'm going to ask you for what are the other possibilities? How else could the roots turn out if the first row of Descartes says 2, 3, 0? We're going to get some more Descartes practice in today's lesson anyway, but let's talk about one of the last tools that we have. It's a really important one. It's called the rational root theorem. What it does is it gives us a list of possible rational roots to test using synthetic division, which I'm going to abbreviate as SD. I abbreviate all these things, by the way. You'll eventually see rational root theorem as RRT, and Descartes' rule of signs is DRS. So as we go through this practice, you'll see a lot of abbreviations from me. So here's an example. If I gave you the polynomial function 2x to the 4th plus x cubed minus 9x squared minus 4x plus 4 equals 0. And I said, all right, let's get a list of roots that even make sense to test in this polynomial, because I don't want to just blindly start randomly picking my favorite numbers like 3 and -2 and 7. I don't want to just pick random numbers and hope that they work. So what we're going to do is we're going to look at the last coefficient, that constant at the end. I'm actually going to call that p. And what I want you to do is for the value p, we're going to take the factors of the last coefficient, and we're going to divide them by q, where q is representative of the lead coefficient. We're going to divide them by the factors of the lead coefficient. And when you divide out all those possible factor combinations, that gives you your list of possible rational roots to test. So if we're thinking about factors of 4, things that multiply to 4, p in this case is plus or minus 1, 2, and 4. Because 1 times 4 is 4, and so is 2 times 2. Why do I write plus or minus out front? It's because it could be positive 1 times positive 4, or it could be negative 1 times negative 4. That got me this number. So we always will write plus or minus there. I'm going to divide that by q, which are the factors of the lead coefficient, which is 2. Well, luckily the only things that multiply to 2 are 1 and 2. So what we're going to do is we're going to take everything on the top and first divide it by 1. Okay, take that list on the top, divide by 1 first. So that's easy. That's just 1, 2, 4. Then you're going to take everything on the top, divide it by 2. So 1 divided by 2 is 1/2. 2 divided by 2 is 1, but that's already in the list, so don't write it again. 4 divided by 2 is 2, which is also in the list. So this right here is our list of possible RRs, possible rational roots. These are the only numbers we would test in synthetic division. So if your favorite number happens to be 3, guess what? I already know 3 is not a root, or negative 3. If your favorite number is 25, you probably wouldn't have tested that anyway. 25 is not a root. It has to be in this list in order to be a possible rational root. Now, there might be other roots here that are irrational or complex, but in terms of the ones that are rational, something that could be expressed as a fraction, whole numbers, integers, things like that, it has to be in this list in order for us to be able to determine the roots of the polynomial. So we are at the point now where we get to put this all together. Putting it all together. Yes, I know you love the math pun there. Or it's not really a math pun, it's a Mr. All pun. Okay, let's solve for all the roots of 4x cubed minus 12x squared minus x plus 3 equals 0. We're going to find all the roots. We're going to think about all the things that we know up until this point, like Descartes' rule of signs, rational root theorem, synthetic division, maybe root location theorem, upper bounds and lower bounds, all those pieces. We're going to try and put it all together right this minute. First of all, what do I know about this? It has 3 roots. A cubic polynomial has 3 roots. So I'm going to be expecting to find 3 answers in the end. I'm going to start with DRS, Descartes' rule of signs. See what types of roots we would expect as far as positives and negatives go. So for f of x, we go plus, minus, minus, plus. And we've got 2 sign changes there. For f of negative x, we'll change the odd exponent terms. That's negative, negative, positive, positive. Only 1 sign change there. So when I go to make my chart, for the cases for positive, negative, and complex roots, the first row of Descartes' rule of signs would say 2, 1, 0. F of x, max number of positives is 2. F of negative x sign changes. At a max, you'll have 1 negative root. What's the other possibility? Like we saw at the start of the lesson, well, if you can decrease any of these columns by 2, which we can do this one, that would make room for other, maybe potentially complex roots. These are the only 2 cases, and what's nice about cubics in general, I'll give you a little bit of a hint, at a max you only have 2 possibilities of how the roots could turn out in the end. So it's either 2 positive, 1 negative, or maybe it'll be 1 negative and 2 complex. All right, let's do the rational root theorem. That's the new test that we're adding on. Rational root theorem says take the factors of p, divide by the factors of q, and those are your possible rational roots. So what is p in this example? P is the last term, the constant. So things that multiply to 3 are plus or minus 1 and 3. Okay, what is q? Q is the lead coefficient right there. So the factors of 4, we did that in the other example, it's plus or minus 1, 2, 4. So to get your list of possible rational roots, it's plus or minus the following. First, take everything on top, divide by 1. So that's just 1 and 3. Then take these numbers on top and next divide by 2. 1/2 and 3/2. And then lastly, take everything on top, divide by 4. So you get 1/4 and 3/4. There are a lot of fractions in our possible rational root list, but that's okay. We don't have to be afraid of fractions. We've got some integer values to test as well, so we can start with those if we feel more confident. But what am I heading to next? We're heading towards synthetic division. And synthetic division, you will only see me model this using the new chart format that we've seen in our notes. So I hope that you're getting used to that. Guys, remember the roots that I'm testing are in this left column. First thing I'm going to do is I'm going to put a 0 there, because testing 0 would just give me the original coefficients of the polynomial at the top, which include 4, -12, -1, and the last number would be the remainder there, which happens to be the y value. So we call that last column f of x. Okay, and there's my chart. So just out of habit, I'll tell you that I typically start by testing 1. 1 is always going to be a possible root to test, by the way, right? Because 1 is always a factor of any number, whether it's at the end of the polynomial or the beginning. So I don't know. I like to test 1. It's usually an easier, like, let's get the party started tester here. So bring down the 4. 4 times 1 is 4, plus -12 is -8. -8 times 1 is -8, or yep, -8 plus -1 is -9. -9 times 1 is -9, and -9 plus 3 is -6. So we might be a little sad because we tested 1 and we didn't find that it's a root. However, there should be big alarm bells going off in your head and saying, wait, what happened there? We went from a y value or a remainder of 3 to now a new y value at -6. When we see a sign change like that, that's a big deal. Really is going to reduce the amount of work that we have because I know there's a root between 0 and 1. I know it for sure. We have to cross the x-axis. So the only issue is that when I look at my list, well, it could be 1/2, it could be 1/4, and it could be 3/4. There's actually 3 choices of what I could test next. Typically 1/2 is going to be a little bit easier to test, so I guess I'll do that one. If 1/2 doesn't work, maybe I'll move on to 1/4 or 3/4. But bring down the 4. Half of 4 is 2, plus -12 is -10. Half of -10 is -5, plus -1 is -6. Half of -6 is -3. Oh, wait, plus 3 is 0. We found a root, which we're very excited about. Now, at this stage, you are done with synthetic division. Don't do any more. Because we have to, at this point, take these 3 coefficients and write the quadratic equation 4x² minus 10x minus 6. Because by the way, if the other 2 roots are complex, you won't find them from this synthetic division process, will you? Or if the other 2 roots are irrational, let's say, right, things that have radicals in them, you won't find them by testing these values. So to save us some time, you can stop once you find a root, write the quadratic, and solve from there. Now the nice thing about this quadratic, by the way, is that everything's divisible by 2, and you don't even have to factor that out as a GCF. You can divide it from both sides. And then ask yourself, is this factorable? And if you're not sure, or if you're not great at factoring with lead coefficients, you can do quadratic formula. But I'm great at factoring with lead coefficients, and I know that it is factorable. There's not that many choices, by the way. You know, it's some combination of 1 and 3. One's positive, one's negative. So if you play around with the factors long enough, you're going to wind up getting that this is the correct factorization. So we get x equals -1/2 and x equals +3 are the other 2 roots. Okay, so a couple things to check in on. Are those possible rational roots, -1/2 and 3? Yeah, remember it's plus or minus anything in this list, and look how 3 is also there. Notice how in the end we have 2 positive roots and 1 negative root. Oh wait, that's what Descartes' rule of signs said would happen as one of the possible cases. So in the end, we can conclude that the roots are at plus or minus 1/2. comma, 3. And you could separate those into two different roots if you want to. It's really up to you. We could even make a relatively accurate sketch based on what we now know. We have a root at -1/2, we have a root at +1/2, and then we have another root at 3. Okay, so I know that the graph's going to look something like this because the lead coefficient at the very start was positive. So with a positive lead coefficient, the tail on the right's got to go up, the tail on the left has got to go down. So here is a really nice sketch as to what that cubic polynomial will look like. Okay. So that being said, let's do one more example. If you want to challenge yourself, of course, you can hit pause and try this one on your own. But I'm going to try x cubed minus 2x squared plus 4x minus 8 equals 0. Okay. So I'm going to go through the same exact order that I went before. Let's do Descartes' rule of signs first. So for f of x, we got plus, minus, plus, minus. We've got 1, 2, 3 sign changes in f of x. Okay. F of negative x would go through and change all the signs of the odd terms. So that's going to be negative, 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 negative. Whoa, 0 sign changes in f of negative x. Descartes' rule of signs is extra helpful in this case, because your first row is going to be 3, 0, 0. Remember, this one only has 3 roots. Okay. The only other way the roots could turn out is if I decrease the positives by 2, it could be 1, 0, 2. But since 0 is the maximum, the most number of negative roots we can get, you will not have any negative roots for this polynomial, only positive roots. Which means when I go to do my RRT, my rational root test, I still write typically that it's plus or minus in the end, the P over Q ratio. But even though it's plus or minus any of those possibilities, I'm not going to test any of the negatives. I just know that they won't work. So let's see, the factors of P are the factors of the last coefficient there. Things that multiply to 8 are 1, 2, 4, and 8. Doing this stuff pretty quickly, but it's just quick to get those factors. We really like when Q is 1, because the only factors of 1 are 1 and 1, right? So therefore, when I take everything on the top, divide by 1, it's just that same list, plus or minus 1, 2, 4, and 8. These are the only numbers I'm going to test, which seems like a list of 8 numbers with plus or minus, but oops, I'm not going to test any of the negatives. So just the positives of each of those. All right, let's keep going. If I talk about synthetic division, we have to start testing some things, right? All right, so put 0 in this spot in the left column. The coefficients are 1, -2, 4, and then -8. Okay. So based on that, maybe I'll test 1 first. I don't know. Maybe I'll get lucky by testing 1. Bring down the 1. 1 times 1 is 1, plus -2 is -1. -1 times 1 is -1, plus 4 is 3. 3 times 1 is 3, plus -8 is -5. Darn, 1 is not a root. I also don't see a sign change, which wouldn't have helped anyway, right? Because if I test, in between 0 and 1, maybe 1/2 would be in that range, but 1/2 isn't even in my list, so it wouldn't make sense. All right, test 2 next. Bring down the 1. 1 times 2 is 2, plus -2 is 0. 0 times 2 is 0, plus 4 is 4, and 4 times 2 is 8, plus -8 is 0. We found a root. Now you get to stop. Do not do any more synthetic division. Remember, this is the coefficient of x squared. This is the coefficient of x. This is the constant. So the x squared equation that we get, even though there's a 0 in front of x, would just be x squared plus 4. Students sometimes are really shocked about what to do here. I shouldn't say shocked, but I see a lot of quadratic formula maybe at sometimes at this point in the process, but you could just subtract 4 to the other side to isolate x squared, square root, and hopefully you can quickly get that the other 2 roots are just plus or minus 2i. So it's not necessarily a factoring technique that we're using there, but you certainly don't need quadratic formula in this case. So based on those as being the other 2 roots, the roots are, in the end, we found x equals 2 to be a root, and the other 2 happen to be complex. So we did get that last row, 1 positive and 2 complex roots. So this is kind of a nice case because I think we found the root pretty quickly. We were able to solve that equation. But I promise next time we're together in class, we'll do more practice with all of these ideas, putting it all together. Because it takes some time to get used to, but I think the next homework will focus a lot on these same concepts. All right, let me know if you have any questions.